Good evening, everyone.
Hi Asia, hey Michael, how you guys doing?
Good evening. I'm good. I'm good.
Right. Giving the others a few to come in, eh?
Okay, sir.
Evening, everyone.
I was just about to ask where you are in the past because I've not seen you for the last couple of classes. Are you okay?
Uh, it's just work. I'm
Huh?
at work right now. I'm saying it's work, and I'm at home. I'm at home. I'm at work right now as well. So just trying to juggle both of them. Juggle work and
All
school.
right. See if you can touch base with Carl, guys. Soon come.
I don't think she'll be able to make it, sir. She told me that she wouldn't be in class today.
You're saying
Yeah, I'm saying Carol told me that she wouldn't be at class today.
she's not coming to class today?
No.
Okay, all right, come in. All right. I, I am back, but I'm
Yes,
also
sir.
under the weather. So I'm gonna ask that you just bear on with me. Somebody had a question?
Yeah. Last week Tuesday you said that you had some coursework for us to do on
Oh,
Thursday.
yeah,
Um,
yeah.
you didn't send it because I
Not
didn't
not
see
at all.
anything.
Not at all.
Okay, I
Because
don't know how much.
by the time me sort out for graduation. Hold on, after all of this, my computer want to charge. Yeah, sorry, yeah, man. So I was saying, um, in preparation for the graduation, I, I just, I dropped everything. When I say dropped everything on the squad metal, it was something else. But anyhow, I have it. I will soon disseminate it. It's not a lot of you.
Sorry, you did
Um,
our happy man still now.
when you saw me,
Graduation, yeah, man. When the Lone Ranger walk up,
no man, trust me. Oh, when Venika walk up,
yeah, man. Yeah, I say at least,
at
yes.
least have one.
The, yeah, the program I graduate every year.
Me say, I'm me fi tell, I don't care how much. At least you know we're well represented. And come next year, me no mega have four. Well,
Yep.
five. Because
Mm-hmm.
Michael J I think
James Stewart.
James Stewart, yeah, Jesus. It's at also. So I should have five. The first cohort of environmental studies students, all of them finished at the same time. Well, two of them didn't continue, but I think we had like five graduating, and it was a nice feeling. It was a nice feeling. So next year graduation is going to be superb. Um, I know I have, I know I have, I should have at least two of the associate students, and five of you. So seven of you, yeah, man. And guess what? When we come here, I don't care what the one to say. I know Paz came for his associates. The rest of you chicken out, but I need to see you guys. I really need to see. So it was a proud moment. One of the things I was saying to some students last night, my calculus students last night, that um having taught a number of those students, and knowing the students and knowing the difficulties that they experience while being students, and seeing that they conquer this feat, it was a proud, proud moment. I am I'm ecstatic. I just love when students excel. You don't have to be bright. You just have to be very determined, very determined. And it was a fulfilling experience for me. Love every moment of it, every moment. So guys, please, one of the encouragements I would give to you is this. And I was going to see this to you past earlier. Matter of fact, I was going to send a message to you. I understand the challenges of this life. I understand, um, work challenges, home challenges, family challenges, financial challenges, and some challenges you just fed up, you just can't bother, you just born done. This is a time when you feel overwhelmed and you feel too relaxed and you miss an assignment. You don't put enough into the assignment and you fail the assignment. This is your final semester, the final semester, an opportunity for you to not just finish off. You are going to be as good as some of the day students because you don't have a summer two. So after this semester, you're done. So I'm saying to you, give it. You have half a semester left. Give 100% of what you have to make this a reality. We started together and we're going to finish it together, right? Finally, one of the things Principal McCarthy keeps saying to me in meetings, we need to increase the number of students in our environmental studies program. And my forever response to him is a number of students are moving away from science because to study science, it takes way too long. Nowadays, people just want a get quick rich mentality. So oftentimes them just going to the BPO because them leave high school, them can't get a BPO work and them start with them own money. And two tools, them want car, two tools, them want house. But as for us scientists, it's a process. It takes some time. And we can't fast track that process. That process just has to run its course. And a lot of students don't want to move on. One of my nephews, I keep saying, he's doing the environmental studies program in Wales. And he says to me, Uncle, I am one of 7 students in the cohort. And him take himself from Jamaica, Ghana, Wales to go study. All right? And it's one of 7 students. So even up in a good foreign, way up north, you don't have many students doing the sciences. And it is just our reality. So what we have to do is to make sure that those students who come in, them go out and we'll hold on upon those and say, you start something, you can't just leave it there. But it is what it is. All right.
Sir,
Any other comment?
sir,
Go ahead.
you know what I said, the courses they start doing now,
Mm-hmm.
especially like when they reach masters.
Mm-hmm.
They add like 2 environmental science courses and then they call like a business master and environmental studies in sustainability and all of that.
Oh
So
yeah.
so
Oh yeah.
what they so because no one is actually going for those courses at the bachelor's level and the jobs are may I tell you, job they out there, whole heap of job they out there.
Mm-hmm.
Good paying job in the environmental studies.
Mm-hmm.
And they need to fill the position. So what they do, they add that and they have a businessman, all right,
Mm-hmm.
environmental, which in fact don't make no sense. You can't have that. But
Well,
the,
well, not quite. Let me tell you what it is that they are doing. Because the truth is, for the principal of a tertiary institution doesn't necessarily have to be an educator. It's really supposed to be a businessman because running a school is a business. So you have to make sure that you know how to cut and carve in order to make things happen. Who should run the school now is a vice principal of academics, somebody now who is so trained in education and has some curriculum instruction under his or her belt and the works. And for me, for somebody who is in for me who hold on one minute, please. For somebody who is in for somebody who is in policy, them going to need a business mind. So those people in sustainable development, Mikey, they're moving into policy. So what you'll find for the masters, they will do quite a bit of policy courses. And they may fling into environmental courses, they say, and them just call it sustainability environment or environment sustainability or whatever it is. And then they go inside here now and they are policy makers. They are not environmentalists, but they are policy makers. And sometimes you and I see the ripple effect of some of those policies that have been implemented. All right. And these are people who have big jobs and and they and a little man like me, who have our training in the field. I say, boy, from grassroots, we have the content. It no work like that. Who are you? I am your boss, and my decision is final because it is going to be over my signature. And this is how now it becomes politicized, like we were talking about last week, and so forth and so on. Yeah. So it is important for us to take that niche, and go there and get into the field and make a difference and make a significant difference. All right. We are at a point in our conversation where um I'm very excited. As a matter of fact, I was going through some past papers and I'm saying to myself, wow, um, we're almost there. Um, we the periodic table took us some time to go through, but it's very important. It's not a lot of you, so I'm sure if I say, brother, we need to, and sister, we need to put in an extra hour here or there, I'm sure it won't be problematic. So it is that we can cover the stuff. I'm not worried. I'm just very excited for you all. What I'm going to be turning my attention to for today's class, it's pretty much of a mopping up of our unit one. Unit one is very long. It's the longest unit, and it is foundational. So I can't just um, skirt over it and say, okay, fine, we're moving into unit two. Reason being, you need to know to write these formulas because I'm going to be moving now into areas such as the lithosphere, the asthenosphere, the hydrosphere. Let me see if I can just bring up these things. I'm telling you, oh my goodness. And we're going to be talking about things like formulas, things that affect share screen. Oh, I'm not sharing? Strange. Thought I was. So we reach all the way down here. Number 12. We looked at some balance equations last week. We looked at ionic covalent and metallic bonding. Identified organic right. So we are somewhere here. We are going to be doing acid-base reactions tonight. So that's where we're going to be doing, and then I am going to do some calculations. Just show you some stuff how things are done. Trying to find the exact stuff, but okay. The specificity of it, number 12, it's under here, the mole concept. So that's what we're going to be looking at today. So all of these here come under one, and then now we're going to move into the hydrosphere. Now in the hydrosphere, we're going to talk about things like the formation of acid rain. There are some formulations that involve that. So you have to know what is happening. The hydraulic cycle. You have to know the formulations for those. The impact of acid rain on building water quality, aquatic life. You have to know that leaching of nitrates. Um, you know, sources of water pollution, pesticide, herbicide, sewage, etc. So we need to know some basic formulas for those. And then when we move into the atmosphere now, we're going to talk about, and incidentally, there is no way you can be doing a course on environmental studies and not come across pollution for quite a bit. So for the hydrosphere, we're going to talk about pollution. For the atmosphere, we're going to talk about the atmospheric pollutants. For the lithosphere, we can also talk about soil pollution. You can't get rid of it because this is what it is that we're doing now in terms of taking care of the environment. So one of the things that I would want you to do and start doing now is just reading up. Start reading on pollution. Just read up. Just anything about pollution, read. Look at different articles. Because something that you would have read, chances are will help you in one of your essays. There is no way you can go through without a piece of something. It may not be a full question, but you may get a piece of something on pollution. You're supposed to eat up that. All right. And then now we're talking about biochemical cycles, carbon, nitrogen, sulfur, phosphorus. Talk about the NPK, nitrogen, phosphorus, and potassium. We talk about our organic materials, inorganic compounds. So I had to spend some time up here. Down here, it's going to be lots of reading on your own, and then coming to have very topical discussions on how it is that we're going to care for the environment. All right. So I have been having some challenges with my internet access. Let me just see something. All right. So because of our limitations, I want to find me, I actually had plans of going to school and doing videoing, having somebody video me doing one of these titrations, and I may very well do that. I may very well do that. All right. Who's using a computer tonight? Anybody? Somebody? All of you?
I use my phone.
Phone.
I'm using a computer.
Okay, great. All right. So I'm going to drop something in your Asia. I'm going to ask you to share this 7-minute video for me. That's okay, Asia?
Sir, that's fine.
Okay, so I just went and just picked up something, a random one. There are so many more online that you can also look at, but I'm gonna actually do one and videotape it and share it with you. All right, so I'll stop share to give you an opportunity to share for me, please.
फ्रेंड्स, मैं हूं सचिन शुक्ला और आप देख रहे हैं ए टू जेड प्रैक्टिकल। सो आज का जो एक्सपेरिमेंट है 11 का एक्सपेरिमेंट नंबर 15 है। इसमें हमारा एम बेसिकली क्या है कि हम पीएच के चेंज के जो इफेक्ट है उसको डिटरमाइन करने वाले हैं।
Sir, is this in English?
I don't think we want to use him because his
Worst accent.
Yeah,
his
we just did
language.
that. That's how it.
But hold on. No, hold on. Let me qualify that. You see, when I know for sure I entered the Department of Geography Geology, UWI Mona to study, many of our lecturers were out of India, and their tongue was very heavy, if you know what I mean. When somebody is speaking and their tongue is heavy, you don't understand what it is that they're saying. So the first class, I was like, oh no, there is no way I'm going to continue with this. And then after the second or third class thereabout, you understand exactly what it is that somebody will come and say, what him saying? Say, oh, this is what him said. Yeah, so you will need to get
फ्रेंड्स
with
मैं
it.
हूं सचिन शुक्ला और आप देख रहे हैं ए टू जेड
No man,
प्रैक्टिकल।
no,
सो
no,
आज
no,
का जो
stop it. Pause it. I'm gonna find
You know, Kundur that usually teach Excel.
yeah.
He taught me maths. And we
All
used
right.
to make fun of him when he said X.
Yeah. It is also try this one, Asia. It is also reality. Try that one, my love. It's also reality. We and if we decide that we're gonna go abroad to do our masters and so forth and so on, or even stay here to do our masters in sustainable development or whatever it is, we are going to find it something like that. And we'll go there to work, we're going to find somebody in the field. Right.
Okay, so today I'm going to be showing you guys how to do a titration. A titration is used to calculate the concentration of an unknown substance. Okay, so we'll need the following apparatus for this experiment. So we'll need a pipette. We have a 25 milliliter pipette here. You'll need a beaker of your titrant, which is your known substance. So in this case, it's NaOH. And you'll need a beaker of your titrant, which is your unknown substance, which in this case is HCl. You're also going to need a beaker for your waste, for when you finished your titration. You're also going to need a conical flask, which we're going to use with the burette. Then you'll need a burette, and the burette we're going to fill with our titrant. And then you're also going to need a white tile, because while we do our titration, we want to see the color of our result. Okay, and then we're also going to need phenolphthalein, which is going to act as our indicator. And then finally a conical flask, which is going to hold our unknown solution. And finally, you're going to need a retort stand to just hold your burette. Okay, so before we start with anything, we need to first rinse all our apparatus. So let's go do that. Okay, so we're using deionized water because it obviously doesn't react. So we're just going to clean our apparatus. Conical flask, make sure to clean inside and rinse. And also make sure to clean the neck. Don't clean your burette because, we're just going to fill it up with our known solution. Okay, so it's important to make sure your burette is closed. Otherwise, your NaOH is just going to flow right through. So we're going to take our NaOH and we're just going to fill our burette, making sure it's closed. And once again, it doesn't have to be at 0, it just has to be at a reading. Now we're going to take our pipette and we're going to take a bit of our unknown solution and place it in the pipette. So this is an automatic pipette. So I squeeze the bulb and then I put it in here, into my HCl. I hold my one valve and it fills up. This might take a while. And if you look closely, you'll see that we must line up our liquid with the line here, and then we know we have 25 centimeters cubed or milliliters exactly. There we go. Okay, and now we can place this in our conical flask. Let's fill up our conical flask. This takes a while as well. And make sure you don't get that. There's going to be a drop of liquid left in the pipette, but don't try to get it out. The pipette's made, it takes that into account. Okay, now we're going to need some indicator, so let's go get that quickly. Okay, for our indicator we're using phenolphthalein, so we're going to use the dropper, and we're going to put in 3 drops of our indicator into our HCl. And that's fine. Cool. Okay, so before we can start our titration, we have to first get our initial reading from our barrette. So if we put a white towel behind, we measure from the bottom of the concave, and we measure to 3 decimal places. So this is about 33.40. Okay, so now we can actually start our titration. So a few things to remember is to open, you must always place your hand around your barrette and then hold the tap. And then with your other hand, you grab your conical flask on the neck and you spin. So we just keep spinning and we open and close the tap slowly and let a few drops go through. And we just carry on doing that. And I already know that there's at least 9 in here, so I open it quite a bit, let it run. And you basically want to carry on until you get a rosy pink. So if we carry on, and you'll see that the pink stays longer the further we go. So you carry on. So you want the rosy pink to stay. Okay, and there we go, we're done. And that's a titration. Okay, so once we've done our titration, now we need to get our final reading of the volume. So if we use the flat tile, you go eye level, remember, 2 decimal places. So that's 48.18. Okay, so after you've performed 3 titrations, and every titration has given you a change in volume, you can come up with an average change in volume, which you can then use to calculate the concentration of the unknown solution. Okay, so in our tests, after 3 titrations, we came up with an average volume of 13.665 centimeters cubed. So we'll be using this volume for our calculations. So the first thing we need to do is we need to create a balanced equation for our experiment. Now there's a nice general equation that we can use where we can just substitute our own chemicals to do this, and that is A number of moles of acid plus B number of moles of base forms a salt plus H2O, and we can basically use this and substitute our own values in there. So we know that our acid was HCl and our base was NaOH. This means that it formed a salt, NaCl. Now what we can go do is, now we can go and balance it. Well, there's 2 H's on the left, 2 H's on the right, that's balanced. 1 Cl left, 1 Cl right, 1 Na, 1 Na, 1 O, 1 O. Okay, so this is already balanced. So that means we have 1 mole of HCl reacting with 1 mole of NaOH to form NaCl and H2O. So now we can use this general formula to calculate the concentration of the acid, and here you can see it here. So now we can go and substitute our values in. So we're looking for the concentration of the acid, Ca. We know that the volume of our acid is 25 because we used a 25 milliliter pipette.
Pause that for me, please.
This goes over the
Bishop.
concentration of our
All right. Thank you. That's not the formulation I'm going to teach you how to do this stuff. So up to the balance equation is good. The concentration of the acid times the volume over the concentration of the base times the volume equals MA. I'm not going to teach that methodology. All right. So thank you much. You can save that video. You can look at other videos. Going to ask you for an opportunity to share, Asia. Thank you very much, my dear.
Mm.
All right. So yes. So let me just talk to you about the video that you saw. So there are several things that we need to have when we're in a titration. You need a clamp and stand. He called it a retort stand. You need a burette. The burette is what you're going to place in that retort stand.
Mm.
You're going to need your solutions. Now, let us look at this question. It asks us to calculate the concentration of sodium hydroxide and sulfuric acid. So we know that our two solutions are sulfuric acid and sodium hydroxide. We have the concentration of the sodium hydroxide. We don't have the concentration of the sulfuric acid. So we have the concentration of a known, and we want to find the concentration of the unknown. In this case, the unknown is sulfuric acid. Sir, how do you know that? Let us go. Calculate the concentration. Well, sorry, it's the other way around. Calculate the concentration of the sodium hydroxide given that 23.5 of this mole per dm cube of sulfuric acid. So you're actually given the concentration of the sulfuric acid. The 0.25 moles of sulfuric acid neutralize 25 centimeters cube of sodium hydroxide. So my known is sodium hydroxide. My known is sulfuric acid, I'm sorry. But my unknown is sodium hydroxide. So I'm going to be using my known in order to calculate the unknown. Last week we spent some time looking at balancing equations. The equation that you just saw a while ago was in a mole ratio of 1:1. One of the things I could say to you, or he could say to you, is that 1 mole of the sodium hydroxide, the base, required 1 mole of the hydrochloric acid for neutralization. So when I calculate the concentration, or the number of moles, rather, of the known, I can therefore say that the unknown contains the same number of moles. Why? Because it's in a 1:1 ratio. It's in a 1:1 mole ratio, right? Very important.
Mm.
So that's why the mole ratio was very important for him to calculate, because he's actually going to be using the mole ratio to determine the concentration of his unknown. So here we are given the concentration of sulfuric acid. So what happened is we're going to fill up the burette with one of the solutions. We're going to be using a pipette. No, he did say that he was using a 25 ml pipette. No, you can use a 20 ml pipette, and you have a 10 ml pipette, you have a 5 ml pipette, Normally in the lab, we use a 25 ml pipette. In the video, you saw a reddish brown looking thing atop the pipette. That is called a pipette filler. When when I was doing CXC chemistry, we were required to suck up the solution through the pipette.
Yeah,
Yes.
that's what I used to do.
Yes. So we had to suck it up. And quite a number of my classmates actually swallowed some of those things that they suck up, because I'm being very kind when I say that they were sucking too hard. All right. And I say this to mean, once you're sucking up and you pass the bulb in the pipette, take time and suck, because what it is that you're sucking through now is going to be a capillary, right? So it's like a straw, but there's a bulb. The bulb is going to take a while to to fill up. So when I'm doing the titration, I normally suck really very hard in order to get it to fill the bulb. Once the bulb is filled, then I decrease the pressure because you don't want to be swallowing the solution. I can't ever recall swallowing any of those solutions or even getting any other solutions in my mouth, right? But some people just don't understand the art of doing it. All right. And then now, when you move to A levels now, and even more so when you move to university, you're not allowed to put your mouth on any of the apparatuses. Nope. Nope. Illegal. All right. So you're given pipette fillers. And I can say to you, many of my classmates never knew how to put on a pipette filler and would have broken one or two of the pipettes because when I fight it to go on and just snap. All right. So when you're in the lab, it takes time. All right. So I want you to go back, not now, but I want to go back sometime soon. Give me half a second, please, guys. Sorry about that, yeah. So, and then now you have your conical flask. Your conical flask is what you're going to be using in order to complete the titration. He used a white tile. Not all the times we use a white tile, but of course, whenever you're using phenolphthalein, I think he called it, pronounced it phenolphthalein. We call it phenolphthalein. We will need to see that color change. And it depends because, in an acidic form, it has one color. In a neutral form, it goes colorless. And then now, we need a bottle of deionized water. We're going to need a beaker for our waste. And we have to wash the apparatuses. We'll have to wash them properly. One of the things that we normally do is whatever solution I'm putting in the burette, I'm going to pour some of that solution in the burette and rinse it with it. So that, for example, the tip of the burette, if it has water in it, when I run my solution that I'm going to put in there, my solution will replace the water that is inside there. So I'm not going to have any dilution taking place. Let me pivot right here and tell you how important what it is that we're talking about. If you're working at say with Cinco that manufacture these canned water or these juices, and they are putting the bricks, which is your sugar, you would agree with me that if the sugar takes long to dissolve, that the first batch of drinks coming off going to be what?
Fresh.
Going to be fresh. It's
Fresh
going to be
like
fresh.
fresh.
Right. And then now, as you go along, maybe the second batch or the third batch going to be what?
A little bit sweeter than the first one.
Absolutely. It's going to be a little bit sweeter. So that's why you have people like quality assurance officers who will ensure that the bricks go in at a correct temperature, so that it dissolves and that, everything is there when the first batch comes off. The quality assurance officer will definitely have to do some sampling. And some of the sampling also involves a taste test. Once it is that you're in the food industry, you have to taste the stuff. So you have to keep your palate clean, because sometimes you may be manufacturing different flavors of drink. So you have to be able to clean your palate so that you know that, I don't know if this happens to you, but I know when my mother is cooking, she don't eat anything because she don't want nothing in her mouth, because she don't want to fool up her taste buds, right? And as a grown man now, I find me doing the same thing. Once I'm in the kitchen preparing a meal, I'm not going to be snacking on anything because I don't want to dirt up my palate, so to speak. It is exactly what happens when we're doing a titration. We have to make sure that things are fine, because if we are making a solution so that we can crystallize to make tablets, aspirin for argument's sake, if we don't go in at the right concentration, it means that when we think that we're taking a 500 milligram, it's not really 500 milligrams we're taking. We're taking more. And what is important, and a lot of people don't recognize this, is when for example, I'm under the weather, so I'm taking cold and flu. The instruction says every 6 hours. I cannot run the process and say, oh, I don't have time to be sick, so I'm going to take it every 3 hours. The danger of that is the concentration within that cold and flu, when dissolved, will definitely have to be passed through my kidneys, because my kidney acts as a filter. Just like when them have a filter funnel there for the experiment, but they never needed. Well, they have a filter funnel there, and the filter funnel, or the funnel, the filter funnel is when I put my my filter paper inside there, so we call it a filter funnel. But my funnel was used in this experiment to place the liquid in the burette. So you have to be very careful, because what you don't want is the solution to become too concentrated. Your kidneys, for argument's sake, as I was saying to you, can come under pressure, because if you don't wait until a period of 6 hours to have passed and you take the medication every 3 hours, you are actually damaging your kidney or your kidneys, and which is why the instruction to your medications must be adhered to. There are some medications that you have to declare, which is why when you go to the doctor says, what are you taking? And if you decide, say, oh, me not tell the doctor, me take nothing here, you may be at risk of developing a blood clot that you can actually die from, because you did not disclose to the doctor exactly what it is that you're taking. So full disclosure must be given to your physician. We're spinning that out there. Right. So you have to be careful. So if the point I'm making is, so if you are not careful in the lab and you're making aspirin, I said, sure, we'll put all that in there. when the patient believes that he or she is taking 500 milligrams, chances are 600 milligrams you're giving the patient, right? And it can cause, problems. And the pharmaceutical industry has had many lawsuits, and they have paid out billions of dollars. It's a mega billion-dollar industry. One of the last or recent pullbacks was Zantac. And there are many others on the market, but Zantac just comes to mind now. And why it is and how it is that they pull Zantac from it? When patients come in and are diagnosed with, varying illnesses, the data is stored. And especially if the patients, coming in and say, boy, case in point, COVID, lots of people were
Mental.
developing. Huh?
Them did I have mental breakdown? You're afraid to say so?
Well, not only mental breakdown, not only mental breakdown, but they're also suffering from myocarditis and pericarditis. It's pretty much heart disease, right? And some physicians come out and just tell you straight up, you take the vaccine, yeah, this will happen to you. And many of them have died because they've had heart attacks. Some physicians not coming out to tell you that this is the case. And some people may say that, okay, Sir Shan, you are irresponsible to say this because you don't have the data. Some physicians say this is what is happening, and some other physicians say nothing is not happening. Some physicians have taken the vaccine and would have said to me, I regret taking it. I regret taking it. And some others are saying that, one of the best things that I have done is to take this vaccine, and all of my family members take it, right? But others are not so fortunate because, of whatever it is. So what happens is when a patient comes in and, the doctors doing the stuff, they can say, oh, what medication are you on? Oh, I'm on Zantac. And you recognize that it may be a malfunction of the liver. And then now, in another clinic or hospital, another patient comes in with a similar something, and it is entered into the database, and in the list of medications that this new patient is taken is Zantac. And I say, okay. And then now, in another part of the country, and I'm thinking maybe in the United States, in another part of the country, in the database, yet another person with a similar malfunction of the liver or the kidney, and they list the medications that the patients are on, that this the third patient on, and there's something that is very common again, Zantac. So what it is that they have done, they've conducted extensive research on the types of medication. So what it is that they have done is to say, all right, get a plan. So out of 100 patients who come in, 90 of them were taking this particular drug. So we are going to pull this drug from the market because there's a cause and effect to the stuff. And then now they will go into the lab and do experiments on this specificity of it. And if it comes out to be positive, then we say the plan. No longer are we making this drug because this is damaging to one's health. This is how important it is for you to be very accurate with what it is that you're doing. Very, very important. All right? Can't overemphasize it. All right. So that is what the experiment looks like. As I said, I promise that I'm going to do one and take a video and send it off. So it is that you can see, a local one. So work with me here now. It says we need to calculate the concentration of sodium hydroxide. That's my unknown. That is my unknown. Given that 23.5 centimeters cube of a 0.25 mole per dm cube sulfuric acid neutralized 25 centimeters cube of the hydrochloric acid, I'm going to ask you, think about it. Which solution I put in which apparatus? And based on what I gave you here in these two lines, tell me which solution I put into which apparatus.
Sure, you put the sulfuric acid in the conical flask and the sodium hydroxide in the burette.
All right, I heard that solution suggestion. Anybody else? Anybody else? Well, matter of fact, not anybody else. I need the other two to participate in this. And it's not a matter of being right or wrong, you know. You're learning this stuff, and I'm taking my time out. And it's kind of difficult to do it because I am not physically in a lab, but I have to go through the stuff. So the rest of you, the other two of you, please, quick and fast.
Sir, but based on all the equation, right? Oh, sorry, you're right. The equation based on how it's placed in the different equipment, different apparatus.
Well, based on how this is written, I can tell you what was placed where. All right. You remember when I spoke about the pipette?
Yeah.
What size pipette I told you they were using in that case and what we normally use?
You normally use the pipette for the acid?
Well, it could be for the it could be the other way around as well. Or we could use for the base. But
Yeah.
what
have base first.
Yeah, but no, but guess what no? What size pipette were we using in that experiment that the young man did just now? What size pipette was he using?
Is that 20? I think it's 20 ml.
25. Right. It's a 25 centimeters cube pipette. Right? So he says a 25 centimeters cube pipette. So tell me now. Read that one sentence there and tell me which solution was placed in the pipette.
Sodium hydroxide. No. Sulfuric acid. Sulfuric acid.
Asia, what you say?
I would say sulfuric acid, the pipette, and the burette will be the sodium hydroxide.
Yeah.
Paz, what say you?
Sulfuric acid.
Sulfuric acid goes where?
Into the sodium hydroxide.
No, man. Sulfuric acid goes where? In which apparatus?
The pipette.
All right, so tell me now.
Sir, hold on. Before you answer, let me read it one more time. It's sulfuric acid neutralize 25 cubic centimeter of sodium hydroxide.
Mm-hmm.
And that to me sounds like the sodium hydroxide actually in the pipette.
And you're well, actually, he's correct. Let me read it for you. Calculate the concentration of sodium hydroxide given that 23.5 centimeters cube of a 0.25 moles per dm cube of sulfuric acid neutralize 25 centimeters cube of sodium hydroxide. So what's the volume of sodium hydroxide that was used?
25
sodium
centimeters cube.
Yeah.
All right. So I'm gonna read it one more time because I want you to be able to see it. I want you to be able to see it. Calculate the concentration of sodium hydroxide. Given that 23.5 centimeters cube of a 0.25 mole per dm cube of sulfuric acid neutralizes 25 centimeters cube of sodium hydroxide. So it suggests, therefore, that the sodium hydroxide was placed in a pipette, in a 25 centimeters cube pipette. And in my burette, I had my sulfuric acid. Follow me?
Hmm?
No, Paz, you not see it?
So repeat the last thing.
No.
It is saying to me that it says it is asking us to calculate the concentration of sodium hydroxide. Given that 23.5 centimeters cube of a 0.25 mole per dm cube of sulfuric acid neutralizes 25 centimeters cube of sodium hydroxide. So the sodium hydroxide, the sulfuric acid neutralize exactly 25 centimeters cube of sodium hydroxide. But how much sulfuric acid neutralized it? It was 23.50 centimeters cube of sulfuric acid was needed to neutralize 25 centimeters cube of sodium hydroxide. So because he did say that we're using a 25-meter pipette, it means that the 25 centimeters. I was correct. I said milliliters a while ago, and then I changed and said centimeters. Milliliters and centimeters it's one of two. You'll see what it's talking about. So I really wasn't wrong when I said that. So 25 centimeters cube of that was placed in the using in the pipette. So the 25 centimeters cube of the sodium hydroxide was pipetted out. So I know what amount I'm going to be using for the sodium hydroxide. The mere fact that it's in is 25 centimeters cube suggests that it's from the pipette.
Sir?
Just go ahead.
All right, so all right, based off of my understanding, because it's saying that the sulfuric acid neutralizes. So it almost it's like it's saying that you have to put the sulfuric acid in the sodium hydroxide to neutralize it. That's how I'm understanding it.
And you are correct. But how much sulfuric acid do you use?
0.25
no.
mole.
That's a how much? What's the volume? What's a very good? 23.5 centimeters cube of sulfuric acid was placed on how much sodium hydroxide has?
25.
Very good. So you're seeing it. So I'm saying to you, the mere fact that the 25 centimeters cube of sodium hydroxide was used suggests to me that the sodium hydroxide was placed in the pipette. That's all I'm asking. That's all I'm saying.
Pause. Pipettes are very accurate. So if it specify a particular volume, then you know definitely. So if it's a 10, 5, 20, 25, and you're working with that measurement, you know, say, yeah, it have to go in a pipette, because pipette literally accurate, or one of the most accurate measuring tool in chemistry.
You follow what I'm saying? So it has to be. So I'm just saying this to say to you that and it may be difficult for you to see what is happening here, but yes, it is going to be that. All right, do me a favor. I'm gonna stop share so that I don't want to. Asia, can you go back to the video for me, please, love? I don't want you to scroll to the point where he was introducing the apparatus.
Known solution. And finally, you're going to need a retort stand to just hold your burette. We're going to type OH apparatus for this experiment. So we'll need a pipette. We have a 25 milliliter pipette here. You'll need a beaker of your...
Right. So that's what I'm saying to you. So he has a 25 milliliters pipette, which is what he's holding in his hand, right? Where his left hand is, which is on the right hand side, not the hand that is holding the reddish brown thing, which is a pipette filler. The other hand is actually holding it by the bulb, right? The bulb of the pipette. Good. So what I'm saying to you, Paz, is I have different calibration of pipette. I can use a 5 mil pipette. I can have a 10 mil pipette. I can have a 20 mil pipette. I can have a 25 mil pipette. Whatever calibration, right? And as Michael says, it is accurate. It is very accurate. In a tool to use. So that's what I'm saying to you. So the mere fact that this is a 25 mil pipette, and in the question that I gave you says 25 centimeters cube of sodium hydroxide was used. So 23.5 centimeters cube of a 0.25 mole per dm cube solution of sulfuric acid neutralizes 25 centimeters cube of sodium hydroxide. It suggests to me then, since that he's using a pipette, that the 25 centimeters cube of the sodium hydroxide came from the pipette. Follow me, Paz?
Yes, sir.
You sure?
Yes, sir.
Asia, you see that one, right, Mom?
Yes, sir. I memorize it a different way. I memorize it that since it says sulfuric acid neutralizing the sodium hydroxide, that means say the sulfuric acid is in the burette and is added to the sodium hydroxide. So it's picked up by the pipette. That's what I remember.
All right. Okay. All right. I'll leave that for now. I'm going to come back to it. All right. You can stop sharing for me. Thanks, my love. and don't feel no way that I feel no way about that, you know. Because I mean, remember, we're learning this in an unorthodox way. So that's why I wanted to spend the time on it. All right. So we know that. So we just did the experiment, right? No, we're not using, and which is why I stopped the video at that point. We're not using his calculation. We're using our calculation. When we read the volume on the burette is telling us that it is 23.50 centimeters cubed. Now, let me tell you something. It's in chemistry. If you want to write in a decimal place, you always use 2 decimal places, especially when you're reading your apparatuses. Now, sometimes they may say to you that it's a 0.258 or 0.253 moles per dm cube. But for sure, when it is that you're doing your calibration and you're reading off the stuff, you can get 2 decimal places. Please, in Jesus' name, don't write 23.5. Because if somebody wants to soak you in this life, say you and somebody in the lab not get along and they want to soak you. You know, people can be very callous, you know. And, you know, when you're in a lab working, you have to have all eyes around you. When you're a cashier or a bank teller, you can't just trust anybody for push them in a till. Somebody told me, a family member told me, she was in the hospital working as a dietitian. And she said that, you know, there were several persons there that are well trained. And one of them didn't like her. Black woman didn't like her. So, you know, she prepared a meal and, you know, everybody raved over how delicious the meal was. And the other chef inside there didn't like that. Quite a bit of accolades was given. So when family member went and did the stuff, chef went and added extra salt to it. And it came out. And the patients couldn't eat the food. And it wasted. And, you know, family member got called up and family member says, yo, you're the plan. A year's me I do this for a year. And I tasted my pot before XYZ. Nothing happened like that. Them say, no, that. And them say, do anything you want to do. Let it go to the head. Because I know I didn't do it. And, you know, the Lord never leaves his people without a witness. And they literally caught the person going again to sabotage another meal. And they call out on the individual and, you know, call up to HR and, you know, reprimand and so forth and so on. What's the point? When you're in a lab working and you're writing your values down, if you wrote 23.5 and don't write this up, if I am mischievous, I can write 23.5. 5. We never normally write 23.5, 2, and 3 because, I mean, when we're using drops from the burette and we already established that the sulfuric acid is from the burette. This 23.5 is from the burette. Now, we never normally read is either 0.5 or 0.05, right? So each drop we estimate to be 0.05 of a solution, all right? But one extra drop can make a big difference. Can make a big difference.
Can cause an explosion.
Which is the point. No, listen to what happened. I can tell you this for a fact because I was part of that demonstration. Plutonium was in the early 90s. There was some talk of using Jamaica, the waters owned by Jamaica, as a bridge to transport some radioactive substances.
The man in Cuba said, nah, pass enough for them water.
Them
I remember
say it nah pass, go nowhere.
Cuba so no
Right?
matter.
And we had a serious demonstration. As a matter of fact, as science students, because we at the university knew how dangerous. We march from you, we come right down to Jamaica House and say, yo, Prime Minister, it can't happen. And I mean, while we were marching down, people were joining us, right? With the kind of stupid cylinder, because, and I said, me the driver, I have nobody, me have to find my way back up there, and it wasn't a nice one. But anyhow, yeah, man, we have to march and protest. I mean, I'm very proud that I allowed my voice to be heard in such a scenario. So the Caribbean region, CARICOM, came together now because it wasn't Jamaica alone, you know. The Caribbean region came together and said, yo, run away with that. Nah, pass through. You know, the difficulty is, as I said to you, that one drop approximates about 0.05 centimeters cubed. One drop from the burette approximates about 0.05 centimeters cubed. One drop. If we get one drop of plutonium into our waters, it can wipe out our life form in Jamaica. It is that dangerous, a radioactive substance. Just one drop. So I'm saying to you, one drop makes a big difference. A big difference. So you have to be very careful. So whenever we're writing our values, we're always going to be writing it to 2 decimal places. Please and thanks. All right? Now, the next thing we're going to be doing is moving to writing our balance equation. And we did some of this last week. We know we're talking about 2 compounds, sodium hydroxide and sulfuric acid. Which is acid?
Sulfuric acid.
Sulfuric, right? Because it says sulfuric acid. So that means the other one is going to be the base. Because we're doing an acid-base titration. Right? So sodium hydroxide is going to be my my base. No, this is very important to know because I want to be able to see how it is that we're writing our stuff. Now, we did our formula writing. I'm pleased with what it is that I saw. And you know, kudos to those of you again who, you know, participated in that exercise. I saw the work and I'm very pleased. Sodium hydroxide, the formulation. Hydroxides, the OH has a -1 charge. Has a -1 charge. So the formula for sodium hydroxide is going to be NaOH. Sodium hydroxide is going to be NaOH. Remember, we talk about sodium. When we're writing sodium, we don't write it as a common N. We write it as a capital N. And the A has to be common, can't be capital, right? When I'm writing my hydroxide ion is written as OH, capital O, capital H. So that's why sodium hydroxide now has Na, and then you have the capital OH. So NaOH is sodium hydroxide. Now, anybody ever used sodium hydroxide before? Let me see if we know who's smart.
What if things we use it for?
Like what? Give me one.
We can get 2 drain cleaner and to make soap. Base to make soap.
Very good. Excellent. So one of the main ingredients in our bath soap is sodium hydroxide. Sodium hydroxide. Very important, right? One of my pet peeves when I was growing up was to bathe with oil of Olay or a Dove soap. Jesus, Father. I can't come out of the bathroom because the skin just feel oily. And I hated it when I was growing up. When I was growing up as a child, I hated it. So you know what me want to do? Me want to be with carbolic, you know, because when me done being my skin supposed to crisp. When I rub my finger upon my skin, it's supposed to squeak. Little did I know that I'm not so it's supposed to do because that is drying out the skin or the oil from your skin. And you don't want that to happen. You want some oil to remain on your body so that it helps to moisturize and to protect your skin, which is what the oil of Olay and the Dove bath soaps do. Right? The other ones, like the Irish Spring and the Zest and the Carbolic, yeah, man. When it's done with, and you rub your finger upon it, so like when you wash glass, and you put and the glass was clean and squeaky clean, I saw your body squeak, right? That's not good. So yes, sodium hydroxide is used for that. And as he said, sodium hydroxide is also used for drain cleaners. Now, when you have your septic tanks, for argument's sake, and you have that high smell, at the corner of the house, from the little, the flow from the bathroom before it gets into the septic. Sometimes it's very smelly because the feces is not flushed down properly there, and like a bite trap, and it all you do is just get some. You can go and buy it, some sodium hydroxide pellets. They come as pellets, right? As a solid pellet, and then you dilute it and you throw it down into the stuff. And trust me, every skid mark that is in that culvert going down is going to be removed. In your toilet bowl cleaner, look at it, it contains sodium hydroxide. So once you spray that big boy inside there, it's going to come out squeaky clean, right? So you've met that one. Now, sulfuric acid, you may not have met per se, but it's one of the mineral acids, so it's very strong, right? One of the things that I want to point out, that I have something that's called AQ. It means that it's aqueous. It means that water is added, right? So I am giving you the sodium hydroxide, but I'm giving you a diluted amount of sodium hydroxide. So even if you use the sodium hydroxide in your pipette, and you pipette in the sodium hydroxide, if it gets into your mouth, it's not going to kill you because it is very dilute. It's very, very, very dilute. So it won't kill you. It will have a funny taste. It might make it taste funny for quite a while, but you won't die. It's not going to kill you. All right? The sodium hydroxide also.
That burn up your mouth. You left after party.
Yeah?
You left after party, it got burn up your mouth.
Yeah, but I mean, if it's very dilute, as I said before, I have many of my friends who will suck up and just run and spit out in the wash basin, and rightly so, because I mean you don't want to swallow it, but it won't kill you. It will just leave a funny taste. But I'm going to give you a concentrated solution to work with, because a concentrated solution is very dangerous, right? I've worked with concentrated solution because as instructor, and I have to use a fume hood. When I'm using a fume hood, I have to literally, it's just my hands alone that, the fume cupboard is down and my hands are inside the fume cupboard, because if it spills, I don't want it to splash on me, because it's one of the mineral acids, as I tell you, and it is very powerful, and it can burn, it can kill. All right. Okay, so if you recognize the sulfuric acid also has AQ at the end, because it is saying to me that I added water to my acid to make it an aqueous solution. Now, if you're going to the lab at school, you'll see some of the bench reagents as sulfuric acid and some of the bench reagents as sodium hydroxide. Now, I'm going to have, in a case like this, an acid plus a base is going to give me salt and water. An acid plus a base is going to give me salt and water. Now, the salt is going to be formed, which is sodium sulfate. The salt is going to be formed, which is sodium sulfate. And sodium sulfate is going to be Na2SO4. And that is also going to be an aqueous solution. Aqueous because everything is in my conical flask now. Everything is in my conical flask. And remember, once I react an acid to a base, my result is going to be salt and water. It's going to be salt and water. Now, what is very important for him to balance his equation, and we did the balancing his equation last week. Let us check and hear me out, because they can give you something like this to do in the exam. They can say, write the equation for this or that, and they will not just write an equation, write a balanced equation, including state symbols. So let's go. How many so we have a left-hand side of the equation and a right-hand side of the equation. We have 1 mole of sodium, and we have 2 moles of sodium. Rock stone, but this no balance, because look here, I have 1 sodium on this side, but how many sodiums I have on this side? Not 2?
Yes, sir.
Good. So right here, so now, supposed to have 2 moles of sodium, right? Because what is on the left-hand side has to be the same thing that is on the right-hand side. Now, the mere fact that I put this 2 right in front of the sodium hydroxide changes what?
Sir, it would have changed the OH as well?
Very good. So it means though that I have two oxygen and 2 hydrogens from the sodium hydroxide. So let us go with the oxygen. Let us go with the oxygen. I have 2 oxygens from this side. How many oxygens do I have from the sulfuric acid?
That's 4.
4. 4 plus 2.
6.
Good. So I have 6 oxygens on the left-hand side. Let us check to see how many oxygens we have on the right-hand side. Sodium sulfate. How many oxygens do I have from sodium sulfate?
4.
I have 4. How many oxygens do I have from water?
1.
4 plus 1.
5.
How many oxygens I have on the left-hand side again?
6.
And how many oxygens I know I have on the right-hand side?
5.
It can't work. So I must have both numbers to be the same. So I have to do something now to my oxygen. I have to do something now to the oxygen in order for them for it to be balanced. What do you suggest that I do? I have 4 oxygens from the sodium sulfate, and I have 1 oxygen from the water. What do I do, you think, in order for me to get? I need 1 more oxygen. What do I do in order to get that 1 oxygen? Put on your thinking caps. I have 6 oxygens on one side, 2 now from the sodium hydroxide, and 4 from the sulfuric acid. And my sodium sulfate now has 4 oxygens, and I have 1 oxygen from my water. I need 1 more oxygen. How do I get that? By doing what?
Share with the SO4.
Let me just highlight that 2 right there. I can't, no, the SO4, remember the formula for the SO4, the sulfuric acid is H2SO4. So that can't go any further. All right,
So, sir,
go ahead.
All right, so the end result is salt and water, so that can't change, right?
Very good.
All right, so we have to work the left-hand side of the equation.
Right. But let me answer the question this way. It may help you out a little bit more. Check to see how many hydrogens you have on the left-hand side.
2. So that was what I was going to say. Would you want to
How many hydrogens you have on the left-hand side?
to 4.
Oh, good. So you have 4 hydrogens on the left-hand side. How many hydrogens you have on the right-hand side?
Only 2.
All right. So what would you do in order to increase that to 4?
Multiply by 2.
Good job. So I'm going to put 2 hydrogens. I'm going to put 2 in front of the water. All right. So you may see it easier now.
Oh,
so now you have 2 hydrogens. You have 4 hydrogens on the left-hand side, and you have 4 hydrogens on the right-hand side, right?
Yeah.
Okay. Let us go back now and check our oxygen. We still have 6 oxygens on the left-hand side, don't it?
Yeah.
How many oxygens now do we have on the right-hand side?
We have 6.
We now have 6. So we would have taken care of that shortfall of that extra that 1 oxygen. All right. Now tell me, how many sulfur do I have on one side? the left-hand side?
1 sulfur.
And what do I have on the right-hand side?
1 sulfur.
So is my equation now balanced?
It is balanced.
Okay. So do I now have a 1-to-1 mole ratio?
Yes, we do.
No, we don't.
Oh, because we have 2
Very good.
yeah.
So we now have a 2-to-1 mole ratio. Has you seen that? Is, are you seeing it? Asia?
Hi. So I was trying to work with you, but I maybe 2 minutes last class. So I'm
Oh yeah,
I'm
that's true.
understanding, but I'm kind of lost with the balancing of part.
Right. So you need to go and check up on that. Paz, how you stay? But you weren't here neither, Paz.
Um, not the Thursday, the Tuesday. Not last week wasn't graduation.
No, it's about last week Tuesday. You weren't here. Were you here last week Tuesday?
Last week Tuesday, yeah, cause we were discussing the homework thing. That's all.
Homework. Okay. Right.
Yeah.
All right. Yes. So that's what we do, Asia. So we're gonna have a 2-to-1 mole ratio. Now, that is going to make a big difference when it is that we're calculating the number of moles of the sodium hydroxide. Do we know the number of moles of the sulfuric acid?
Um, 0.25.
Excellent. So the concentration of the sulfuric acid is going to be 0.25 moles per dm cube. Follow me? That is my known. And I don't have the concentration of my sodium hydroxide. And I now want to calculate the concentration of the sodium hydroxide, but I have to use the mole ratio because my sodium hydroxide reacts with my sulfuric acid in a 2-to-1 mole ratio, making it I'm going to be using that mole ratio now in order to determine the number of moles of my unknown. Which is my unknown again?
Sodium hydroxide.
Sodium hydroxide. Very good, very good. Now, this is math, you know. This is math now. If I am saying to you that the mole ratio is a 2-to-1, 2 moles of sodium hydroxide is required, is reacting with 1 mole of sulfuric acid for neutralization. So when he used the phenolphthalein as the indicator, the color change would have told us exactly where the endpoint is, the exact amount of sodium hydroxide needed to neutralize the sulfuric acid, right? So that's why we use an indicator. The indicator tells us the endpoint, and we have many of those indicators, right? Now, if I know that the concentration of the sulfuric acid is at 0.025 moles per dm cube, I'm going to have, let me spotlight, I'm going to have under here, my sulfuric acid is going to be 0.025 moles. How many moles of sodium hydroxide reacted in that acid-base titration just now then? The mole ratio is 2-to-1. 2-to-1. 2 moles of sodium hydroxide reacted with 1 mole of sulfuric acid. The concentration of the sulfuric acid is 0.025 moles per dm cube. How many moles reacted with the...
0.50.
Okay, so it'll be 2 times as much. That's what they said.
Yeah.
Okay, all right. Paz, what say you? Asia, what say you?
I also 2 times the
You say what?
0.25.
No, it's not a 1-to-1 mole ratio. No. Had it been a 1-to-1 mole ratio, yeah, the same number of moles would react in both. But it's not a 1-to-1 mole ratio.
0.250.
How you get that though, Paz? How you get that?
It's not the sulfuric acid.
Mm-hmm. Yeah, man, the sulfuric acid is known as 0.25. But so we know that look at the screen. The H2SO4, we know that is at 0.025 moles per dm cube. But I'm
Yeah,
saying to you now, I want to see how many moles of the sodium hydroxide reacted in that reaction.
because it's cube, no so?
Not cube, how many moles reacted?
It's
Look at the
2.
mole. Very good. So I'm going to need 2 times more of the sodium hydroxide than I would the sulfuric acid. So therefore, so that's why Michael says it's going to be 0.50 because I'm going to multiply 0.25 by 2. You see that?
Yes, sir. Yes, sir. Yeah.
Yeah. Asia, you see that now?
Yes, sir.
So what it is that I've done now is to look at the number of moles of the sodium hydroxide that reacted. Remember, my sodium hydroxide was my unknown, don't it?
Yes, sir.
Good. Right. Sodium hydroxide. Good. So I am sensing a level of discomfort in either balancing the equation, in either writing the equation, balancing the equation, and then using the balance equation now to determine the mole ratio, and then using the mole ratio now to determine the number of moles in one as opposed to the other. Explain to me. Let us have a conversation because I don't want to come back to this one. So tell me, and you must know how to write your balance equation, including your state symbols. You must know how to write your balance equations, including your state symbols. So tell me, what is your level of difficulty in understanding what is required of you in this regard?
More like balancing the equation.
More like balancing the equation. All
Mm-hmm.
right. Okay. All right. So when I give you that assignment, we need to study the first 20 elements of the periodic table from hydrogen all the way down to calcium. Hydrogen mean 1, calcium mean 20. You have to know the mass number. You have to know the atomic number, the proton number, the number of neutrons. You also have to know the electronic configuration of each of those atoms, right? You have to also know the valence electrons and the valence electrons are the electrons that do what? Michael, valence electrons are the electrons that what?
The valence electrons.
What are they? Who are they? What they do?
Uh, those are it has when I remember off the top of my head, but I think they have something to do with valence. The outer electrons.
Yeah, they're the outer electrons, but what they do? They are the ones that what?
Or them actually jump ship.
Right. So they take part in the chemical reaction. All
Yeah.
right. So you have to remember no. So you have to look at things like what type of bonding that takes place to know if it is going to be a total give up or it's going to be a shared relationship. Um, and you know that your group 1, group 2, group 3 are your metals, your alkali earth metals. And you know that those are the ones that give up electrons. They don't share it. It's easier for them to give up than to accept in order to obtain that stable octet. All right. So you know you're giving up those electrons. So if you look at the hydroxide ion, remember now, when we talk about ionization, you have a cation and you have an anion. The cation are those that are positively charged. Those are your metals. The anions are going to be your non-metals. So when you look at sodium hydroxide, you're going to see it's NaOH. So sodium is what number? What is the protonic number for sodium? Come on, you're supposed to know this. Sodium is what number element? But we have been doing a lot of
11.
examples. Yes, but it takes too long to tell me 11. We have been working with these things, man. You need to know this, right? So, so sodium has 11 protons. What's the electronic configuration of sodium?
281.
2,8,1. Very good.
Yeah.
How many valence electrons sodium has?
1.
Very good. 1. So therefore, sodium is going to give up that 1 electron as opposed to accepting 7 other electrons, don't it?
Yes, sir.
See, good. So when sodium gives up that 1 electron, what ion, ION, is formed?
A positive cation.
Positive cation. So it's going to be Na plus. All right. Now, when you look at the OH, the hydroxide ion is an anion, and it's going to be a -1. It's going to be a -1, right? So if you write your sodium, Na, and you put your cation charge underneath the sodium, Na, and underneath it, you put +1. And for the hydroxide ion OH, underneath it, you're going to put a -1. And remember, we did the switching around or the cross multiplication. You're going to end up with Na1, OH1. But just like in mathematics, you don't write 1x, we just simply write it as x. We're not going to write Na1 and OH1. We're just simply going to be writing NaOH. And that's how we get the formulation for the sodium hydroxide. Follow me? Mike, you should know this, because you were here last week. Paz, you were
Yeah,
here
man.
last week?
I'm following. Yeah, man. I'm
Okay.
following.
All right. Let us look at, and I'm only going over because of the discomfort that I'm sensing in going through the question, because we don't reach to the part where we calculate the number of moles yet, We don't reach here so yet, and we have about 5 minutes left, so we don't reach here so yet. Let us look at the sulfuric acid, because you see, you're going to need to know to write these formulas on the exam, because as I said before, when you look at the atmosphere, when you look at the lithosphere, when you look at the hydrosphere, what is a common thread in all of those? I showed it at the start of the class. What is it? There is a topic that comes into the hydrosphere, the
Pollution.
atmosphere, pollution. Pollution. So what is a lithosphere, incidentally? When we talk about the lithosphere,
Earth
what are we
crust.
talking? Huh?
The crust. The land.
Yeah. Where we walk on. Huh? When you talk about the hydrosphere, what is that?
Water bodies.
Yeah. And of course, you know what the atmosphere, and you know what the atmosphere is. So um which cartoon talk about earth, wind, and fire again? Earth. Fire.
Avatar.
No
Captain
man.
Planet.
Avatar.
No man,
Captain
Avatar.
Planet.
Captain Planet. Yes, right. Yes, right. Earth, wind, fire, right? Yeah, man. So those are the. So I want you to look at my sodium, my sulfuric acid now. Look at my sulfuric acid and tell me what you think the SO4 charge is. Just look at what I have there. H2SO4, and my SO4 is the anion. I want you to tell me what charge is on the SO4. What do you think the charge is? Let me see if you're understanding.
Sorry, what was the question?
We're looking at the sulfuric acid, the H2SO4, and I'm asking you, what charge do you think the SO4 is? Like what I said, that the OH has a -1 charge. I'm saying
Yes,
to you that
sir.
I'm saying to you that the SO4 is an anion. So I'm asking you, just look at the formula, the H2SO4, and tell me what charge you think the SO4 has.
4.
Look at the formula.
Um, it would have basically accept, so -2.
How did you get that? Or why did you say -2?
Sir, because the sulfur atom, it has 16 protons with an electronic configuration of 2,8,6, I think. That's it.
Mm-hmm.
And the sulfur, the oxygen would be 6. The oxygen is 8, which is 2,4.
Mm-hmm.
So for you to form the SO4, you would have to get 4 oxygen who is willing to share with the sulfur, if it make no sense.
Okay. Well, you can work it out like that, but you just stop off halfway. So you don't finish your discourse. There's just halfway that you stop right there now. So you're on the right trajectory, but you still have
The H2,
the what?
I still have the H2 to deal with.
No, I thought you were gonna give me the answer. All right, look at it. You see the mere fact that I have this subscript 2 by the H tells me that this SO4 is a 2 minus. You follow me?
Yeah.
You see the mere fact that I have this 2 at the NA, it suggests to me that this SO4 is going to be a 2 minus because of the crossing over of the thing. You see the mere fact that I have this 2 at the hydrogen tells me that my oxygen is going to be 2 minus. But you already know that oxygen is 2 minus because oxygen has 8 protons, 2 on the first shell and 6 on the second shell. And it's going to need 2 more electrons in order for it to be stable. So it's going to be an O2 minus arrangement, don't it? See the 2 right here, so that 2 as a subscript tells me that it's going to be there. All right, I am not going to go any further with the question. I'm going to ask you to do something for me. What I'm going to do, I'm gonna just fix up the truth of the matter is from last Tuesday I didn't get the chance to look at the stuff for the graduation. I mean, to send off for you the evening of the graduation. I remembered, but so many things were at play, and to get done, and the activities that I was so involved in there. And then I had another function following the graduation. Um, I want you to start reading, guys. Look at rewatch your videos. I want you to start reading. Sorry.
Sir,
I want
you
you to
say
start.
read the slides.
I said read. I say start reading, guys.
Oh, reading guides. Oh.
Guys, GUIS.
Guys.
Oh, start reading, guys. Oh.
Okay. I want you to start reading, students.
Oh, okay.
Right. So you have the
So we're
outline.
reading from any textbook?
You can, or what it is that you do, go back and look at the videos, and then from the videos now you can go and research it. So like for example, I did the formula writing because you see you have to be guided with the textbook, because it's not everything in the textbook that I'm gonna go through, right? So it's just different areas from the text that I'm gonna be looking at. So for example, when we talk about formula writing, you can use any CXC book to see how they do formula writing. This is an acid-base titration, which is why the gentleman was able to say that it's going to be a salt and water, because we know when we do an acid-base titration, we get a salt and a water. We get a salt and water that is formed, right? When I react a metal with an acid, I'm going to get a salt and hydrogen gas is going to come off. I'm going to react an acid with a carbonate. I'm going to still get a salt. So all of them going to give you a salt. With the carbonate this time, I'm going to get carbon dioxide coming off, but I also get water coming off. All right? So what I'm saying to you is, if you remember from geology when I was teaching you with the labs, and I said to you that, you're going to have maybe a container, a squeeze bottle container with either hydrochloric acid or sulfuric acid in it, and you squirt some of it on one of those rock exposures, and it start to fizz. You know that you've picked up a carbonate, because that fizzing part that is coming up is really your carbon dioxide, your gas. So we say that it effervesces. You know, I can buy one soda, I open it and I say, psh, and it's like all, well, Carol not here, but with Craven, Carol was there now, and she run with the soda, and then she reached now and said, yes, Mikey, me reach. And Mikey said, go and drink your soda now. She said, yeah, man, I should open my soda, psh. Right? That's what we call effervesce. Right? So the effervescence would be great because you're running and you're shaking up the soda. All right. So I want you to start your own preparation. God's willing, on Thursday, I'm going to be wrapping up here. I'm going to give you something to read. I'm going to send you something, a notification for you to do some reading for me. All being well, next Monday, I'm going to be going through the other X sections. I have 3 more sections to look at: the atmosphere, the hydrosphere, and the lithosphere. Right? It's really, those are not difficult. You just have to go read and understand. And we're going to have lots of conversations on those. All right. Big up on yourself. Have a good one.
Same to you, sir.
Cool.